Just because you collected some data does not mean you have reached a firm conclusion. Data requires interpretation. Take, for example, the clear correlation between ice cream sales and shark attacks. The graph shows correlation, but it does not tell you the cause. What do you think is the most reasonable explanation for the correlation? One of the most important aspects of data analysis is statistical significance. You don't want to make personal judgment about your data. Instead, you want to use math to determine whether you collected enough data to reject your null or not. For example, imagine your friend goes fishing at 2 ponds and graphs the results. They ask you which pond has more fish. You might think the obvious answer is pond 2, but the answer actually depends on some critical missing information. Let's add values to the y-axis. Your friend caught 1 fish at pond 1 and 2 fish at pond 2. If your friend spent an extra hour fishing and caught just 1 more fish at pond 1, the results would look different. In other words, your friend has a low sample size, and this could throw off the results because random chance plays a larger role in the outcome of the data when sample sizes are low. What if, instead, the numbers look like this? You should have more confidence that pond 2 really has more fish in it. But how many fish do you need to catch before you can be confident? Is 30 fish enough? 100? Fortunately, there are mathematical ways to figure this out. The field of statistics uses probability theory to determine how confident you should be about your data based on how much you collected. If you caught 962 fish, you can be 95% confident that your sample size truly represents reality. But there is still a 5% chance it is due to random chance, and therefore an error. To have just a 1% chance of reaching your conclusion by error, you would have to catch over 5,000 fish. That could be very time-consuming. The pond may not even hold that many fish in it. In most scientific studies, a 5% chance of error is considered acceptable. But some fields require lower error rates. For example, clinical trials of medicines and vaccines have higher standards because the risk involved in making an error could cost human lives. Drugs need to be safe for the consumer before put on the market. But with thousands of new drugs being authorized for use each year, it is no surprise that a few end up not working as expected and causing harm despite studies showing statistical significance, since each study has a small chance of reaching their conclusion based on errors or random chance. Imagine someone wanted to convince you that aliens existed. Photos are a form of evidence, but they can be faked or misinterpreted. What are the chances that many unexplained photos of aliens exist without aliens actually existing? Pretty small, but the problem is that very few of these photos exist. So sample size is too small to be convincing. News reports are biased by the reporter, whose agenda is to sell papers. But again, many separate reports that fail to be identified as hoaxes could be convincing. Graphs usually include lots of data, but they must be correctly interpreted with statistics. A graph may show a trend that is not statistically significant and therefore misleading. Experiments focus not just on anecdotal evidence, but physical tests, and a good experimental will determine how much data they need to collect before starting the study to assure their results will be meaningful. In other words, the goal of statistics is to rule out the impact of random chance. If you flip a fair coin once, the chance of it landing on heads is 50%. The chance that you will get heads 5 times in a row is low, but it happens occasionally. The chances of you getting heads 100 times in a row and the coin being fair is very improbable. The more you flip the coin, the closer your results should be to telling you that there is a 50% chance of each outcome. It is rarely possible to count or test every individual. If you wanted to know how many people in Africa have red hair, you probably can't go door to door and record the results for 1.2 billion people. You also don't want to get off the plane and base your sample off of the first person you see. Small samples are less likely to be good representations of the population. And low sample sizes can result in false conclusions. False positives are when you reject the null hypothesis incorrectly. A man, for example, could pass a pregnancy test because of an anomaly in the test. Perhaps he ate a rare food that causes the test to malfunction, or has a genetic disorder that causes his body to produce unusual chemicals. There is also the possibility of falsely accepting the null hypothesis, such as a pregnancy test failing to tell a pregnant woman she is indeed pregnant. She could have failed to correctly follow directions while taking the test, or there could have been an error in manufacturing the test. In both cases, taking several tests of different types should lead to the correct answer. If not, it suggests a bigger and perhaps more interesting problem. Even when statistics are used, How to interpret the results can be tricky. For example, it is true that the average person has one testicle, but this is due to incorrectly grouping males and females in the same analysis. It is also true that 100% of people who breathe die, but like in the first example, this is a correlation rather than causation. Misleading correlations are easy to find, especially when searching through large amounts of data. This is sometimes referred to as p-hacking. This sort of data mining has discovered correlations between random variables like the per capita consumption of cheese and the number of people that die by becoming entangled in their own bed sheets, or the number of people that drown in swimming pools and the number of films with Nicolas Cage. Here are some more ways that statistics can be misinterpreted.
Statistics are persuasive, so much so that people, organizations, and whole countries base some of their most important decisions on organized data. But there's a problem with that. Any set of statistics might have something lurking inside it, something that can turn the results completely upside down. For example, imagine you need to choose between two hospitals for an elderly relative's surgery. Out of each hospital's last 1,000 patients, 900 survived at Hospital A, while only 800 survived at Hospital B. So it looks like Hospital A is the better choice. But before you make your decision, remember that not all patients arrive at the hospital with the same level of health. And if we divide each hospital's last 1,000 patients into those who arrived in good health and those who arrived in poor health, the picture starts to look very different. Hospital A had only 100 patients who arrived in poor health, of which 30 survived. But Hospital B had 400, and they were able to save 210. So Hospital B is the better choice for patients who arrive at hospital in poor health, with a survival rate of 52.5%. And what if your relative's health is good when she arrives at the hospital? Strangely enough, Hospital B is still the better choice, with a survival rate of over 98%. So how can Hospital A have a better overall survival rate if Hospital B has better survival rates for patients in each of the two groups? One study in the UK appeared to show that smokers had a higher survival rate than non-smokers over a 20-year time period. That is, until dividing the participants by age group showed that the non-smokers were significantly older on average, and thus more likely to die during the trial period, precisely because they were living longer in general. Here, the age groups are the lurking variable and are vital to correctly interpret the data. In another example, an analysis of Florida's death penalty cases seemed to reveal no racial disparity in sentencing between black and white defendants convicted of murder. But dividing the cases by the race of the victim told a different story. In either situation, black defendants were more likely to be sentenced to death. The slightly higher overall sentencing rate for white defendants was due to the fact that cases with white victims were more likely to elicit a death sentence than cases where the victim was black, and most murders occurred between people of the same race.
Ultimately, we say garbage in, garbage out. If you have bad data or not enough data, your statistical analysis should tell you that. If your data was collected well and you have a lot of it, there should be no way to reach a false conclusion by someone who has a good understanding of statistics. Misinterpretation usually comes from people with an agenda that are trying to mislead an audience. But I don't want you to walk away from this lecture thinking statistics can be interpreted however somebody wants. If you understand statistics, you cannot be fooled, and using statistics is a great way to avoid bias because you must believe what your data shows, whether or not you like the outcome. Here are some descriptive statistics, averages, for the ways that Americans die each year. I want you to notice that there is a difference in perceived dangers like terrorist attacks and more serious concerns like armed toddlers, lawnmower accidents, and death by falling out of bed. We must, as a society, focus on data rather than our unfounded beliefs. This week, you will be conducting your own analysis of M&Ms. You would assume that all colors are created in equal numbers, or would you? You are going to test this assumption and eat your data. Graphing the results is helpful, but you need to include some statistical significance onto the graph in order to make sense of it all. In this case, I have added letters that represent significant differences. Blue has the only A, so there are more blue M&Ms than any other color. Orange, green, and yellow are tied for second, and brown, yellow, and red are tied for third. Notice that yellow is not significantly different from both second and third place. How do you determine what graphs to make and what statistical tests to run? It depends on what type of data you have. There are two main types: quantitative, which is associated with numbers, and qualitative, which is descriptive and categorical. Grouping people into young, middle-aged, and young would create qualitative data, while using age would be quantitative. When you have two variables that are quantitative, you should display that data as a line graph, not a bar graph. Bar graphs are best when there is at least one qualitative variable. Pie charts are used when you're examining the different percentage of variables that add up to 100%. Line graphs show whether data is correlated or not. A positive correlation means both variables increase and decrease together. A negative correlation means one variable increases as the other decreases. If no line can be used to clearly explain the data, or one variable does not change, we say there is no correlation. Again, you need to be able to read a graph in order to understand it, and graphs can be misleading. Here are some examples.
A toothpaste brand claims their product will destroy more plaque than any product ever made. A politician tells you their plan will create the most jobs. We're so used to hearing these kinds of exaggerations in advertising and politics that we might not even bat an eye. But what about when the claim is accompanied by a graph? After all, a graph isn't an opinion. It represents cold, hard numbers, and who can argue with those? Yet, as it turns out, there are plenty of ways graphs can mislead and outright manipulate. Here are some things to look out for. In this 1992 ad, Chevy claimed to make the most reliable trucks in America using this graph. Not only does it show that 98% of all Chevy trucks sold in the last 10 years are still on the road, but it looks like they're twice as dependable as Toyota trucks. That is, until you take a closer look at the numbers on the left and see that the figure for Toyota is about 96.5%. The scale only goes between 95 and 100%. If it went from 0 to 100, it would look like this. This is one of the most common ways graphs misrepresent data, by distorting the scale. Zooming in on a small portion of the y-axis exaggerates a barely detectable difference between the things being compared. And it's especially misleading with bar graphs, since we assume the difference in the size of the bars is proportional to the values. But the scale can also be distorted along the x-axis, usually in line graphs showing something changing over time. This chart showing the rise in American unemployment from 2008 to 2010 manipulates the x-axis in two ways. First of all, the scale is inconsistent, compressing the 15-month span after March 2009 to look shorter than the preceding 6 months. Using more consistent data points gives a different picture, with job losses tapering off by the end of 2009. And if you wonder why they were increasing in the first place, the timeline starts immediately after the U.S.'s biggest financial collapse since the Great Depression. These techniques are known as cherry picking. A time range can be carefully chosen to exclude the impact of a major event right outside it. And picking specific data points can hide important changes in between. Even when there's nothing wrong with the graph itself, leaving out relevant data can give a misleading impression. This chart of how many people watch the Super Bowl each year makes it look like the event's popularity is exploding. But it's not accounting for population growth. The ratings have actually held steady because while the number of football fans has increased, their share of overall viewership has not. Finally, a graph can't tell you much if you don't know the full significance of what's being presented. Both of the following graphs use the same ocean temperature data from the National Centers for Environmental Information. So why do they seem to give opposite impressions? The first graph plots the average annual ocean temperature from 1880 to 2016, making the change look insignificant. But in fact, a rise of even half a degree Celsius can cause massive ecological disruption. This is why the second graph, which shows the average temperature variation each year, is far more significant. When they're used well, graphs can help us intuitively grasp complex data. But as visual software has enabled more usage of graphs throughout all media, it's also made them easier to use in a careless or dishonest way. So the next time you see a graph, don't be swayed by the lines and curves. Look at the labels, the numbers, the scale, and the context, and ask what story the picture is trying to tell.
What is misleading about the second graph? The type of data and the number of variables also determines what statistical test you need to use. You may have heard of regressions or chi-square tests before. If not, they are methods that use math to determine if your data supports your hypothesis. I'm not going to ask you to remember these tests or know how to do any math, but I do want you to know how to interpret the results. Luckily, that means you just need to know the meaning of a single value called a p-value. The value is the output of all statistical tests. It is a value from 0 to 1 that evaluates the probability of rejecting the null hypothesis correctly. Since in biology, we like to have less than a 5% chance of error, we look for a p-value that is at most 0.05, the equivalent of a 5% chance of error. If this is the case, we say the results are statistically significant because we rejected our null hypothesis. Take this first example. Looking at the graph, Rick talks more than any other character on the TV show Rick and Morty. But does he really talk more than Morty? A statistical analysis of the question gives a p-value of 0.01, which means yes, Rick talks more than Morty, with a 1% chance that these results are false and based on not enough data. How would you interpret these results? The null hypothesis is that ratings have not changed over time for Rick and Morty. You might wonder why statistics is so important in science. For one, when you get larger data sets, it starts to be difficult to interpret data. In this experiment, researchers tested 2 vaccines by seeing the numbers of cases of flu for those vaccinated versus those not vaccinated. Staring at the numbers is not obvious whether they both work or not. Including a p-value gives a clear picture. Vaccine A works and vaccine B does not. We use statistics in ways you may not realize. Weather patterns are predicted using statistics. A Google search uses statistics of how much time people spend on different websites that determine what your search results look like. Unemployment is hard to measure, but global economics is understood by examining this statistic. Do you count people who leave their job? This would not account for people who never get a job. Are teenagers and senior citizens unemployed? In 1937, statisticians defined unemployed as people who were not working in the previous week, but were searching for work, and used census data to estimate the number. And of course, knowing what foods and drugs are healthy and safe versus ones that are harmful is all based on statistics. Early data comparing countries where the average person wore a mask and ones that didn't supported the hypothesis that mask wearing is a simple way to avoid coronavirus. One more example. This analysis of different types of masks examined the number of viruses that could potentially be spread. Which of the following statements accurately interprets the results?